Imagine you need to tell someone about a color, but you can only send numbers. You might pick RGB values, or a name like navy, or a short code used in a particular paint catalog. Each choice encodes the same idea, color, but it carries different amounts of meaning. Some encodings are precise about how the color looks on a screen. Others are compact and easy to store. A few are only meaningful inside one company's paint system. That trade-off, how we turn meaning into symbols so machines can store and move it, is what I mean by semantic encoding. It's the bridge between the real-world concept and the digital representation we use to work with it. Let's start with a concrete scene. You inherit a dataset with a column called status. The values are 0, 1, and 2. At first glance, it's tidy. Small integers are efficient to store and fast to compare. But what do those numbers mean? Without a guide, one could be active, pending, or flagged. The encoding is terse. The semantics are hidden. Encoding is everywhere in data. Sometimes the meaning is obvious because the encoding looks like the thing it represents. A date column stores a date. Other times, the encoding is a compact proxy, an integer for a category, a hash for a user identifier, a short code for a currency. In recent years, we've also added encodings that are less literal. Dense vectors produced by models capture semantic similarity, but are not human-readable. Each encoding makes a trade. Human-readable text is easy to inspect and understand, but it can be large, noisy, and fragile to spelling. Short codes are compact and efficient, but they are opaque. Numeric encodings can be fast to process, but they are easy to misuse if the mapping is lost. Embeddings capture nuance and similarity relationships, but they hide the original provenance and require machinery to interpret. When you choose an encoding, think about the next person who will use the data. Will they expect to read the value directly, or will they always transform it? If humans need to inspect it, prefer readable fields alongside compact ones. If machines are the primary consumers, make sure mappings are discoverable and versioned. Two kinds of encoding decisions appear again and again: categorical encoding and numeric representation. Categorical fields often tempt teams to pick tiny integer codes. They are efficient, joins and indices run quickly. But those codes require a dictionary. Without it, the data's meaning evaporates. A safe pattern is to keep both the code and the canonical name. For example, status code equals 1 and status label equals active. That combination preserves compactness and discoverability. It also makes life easier when the code set evolves. New codes can be added without breaking human understanding. Numeric choices hide subtler traps. Units are an encoding decision that silently shapes meaning. Storing lengths in meters or millimeters is an architectural choice. It matters when datasets from different teams meet. The more explicit you are about unit metadata, the fewer conversion errors you will see downstream. Textual encodings carry a different set of trade-offs. Free-form text is expressive and captures nuance, but it is messy to analyze. Controlled vocabularies and enumerations restrict options so meaning stays consistent. That consistency helps automation. There is value in using human-centered encodings. Clear strings or structured objects are often better than cryptic tokens when people explore the data. Then there are richer encodings. Graphs, ontologies, and embeddings. Graph encodings let you state relationships directly. For example, Alice manages Bob becomes a link. Ontologies add layers of typed meaning. A product category can become a node with parents and attributes. Embeddings map items into a continuous space. In that space, closeness approximates similarity. These encodings are powerful, but demand careful documentation. What does proximity actually mean? What data trained the model that produced the embedding? Without that context, the vectors are inscrutable. A recurring mistake is treating encoding as a purely technical decision. It gets framed as what is fastest or what compresses best. But encoding is first and foremost a semantic decision. The choice embeds assumptions about how the data will be used. It reflects who will read it and how it will evolve. A few practical habits make encoding robust. First, record the mapping where the data lives. If 0 means new, 1 means in progress, and 2 means done, store that mapping in the schema or data dictionary. Make the mapping executable. Pipelines should validate that codes only come from the supported set. When encodings change, version the mapping and provide migration notes. Second, favor duplication when it helps clarity. Keep both the lean representation and a readable copy. For example, currency code and currency symbol. Or use a hash and the version of the hashing method. The extra column buys inspectability and faster debugging. Third, think about extensibility. Encodings that assume a closed world break when new categories appear. If you use integer codes, plan for an unknown or overflow bucket. If you adopt an ontology, choose one that can evolve without invalidating existing data. Fourth, propagate provenance. If an embedding was produced by a model, store the model version alongside the vector. If a label was assigned by a human or a heuristic, record that too. Encoding without provenance is like writing in an unknown language. Fifth, align encoding with governance. Privacy-preserving encodings such as hashing or tokenization change what you can do later. If you hash emails to create identifiers, you may lose the ability to recover the original text. Make those trade-offs deliberate and documented. Finally, test your encodings. Build small checks that assert expected mappings exist. Confirm that units match declared metadata. Ensure embeddings fall within expected ranges. Verify that controlled vocabularies have not drifted. These tests catch accidental changes before they affect users. To close, think of encoding as a conversation between people and systems. The symbols you choose are messages. If you make them opaque, future readers must reconstruct your intent from fragments. If you make them explicit, with labels, provenance, and versioning, the conversation stays clear. Semantic encoding is less about packing data tightly. It is about preserving meaning, even as data moves, changes, and ages. Thanks for watching. See you in the next one.